Okay, and now for one of the coolest fractals of all time, the Mandlebrot set. Benoit Mandlebrot lived from 1924 to 2010, and he initially thought his computer had made a mistake, was broken, when he first discovered the Mandlebrot set. He was working with the complex plane. We didn't quite talk about these numbers before. It is a real number plus some real number times I, where I is the imaginary number, the number that squares to be -1. It's not a real number. Positive numbers have positive squares, negative numbers have positive squares. Nothing has a negative square in the real numbers, but it's this imaginary crazy number. Anyway, the complex plane is a way to depict all of these numbers. You have the real part and you have the imaginary part. And so here is I, here is 2 times I, here is -I, here's 2, and you have combinations. Now, normally on the plane, this is a pair of numbers. But in the complex plane, this is a single number, 2 plus I. This is a single number, 3 minus I. Anyway, he did this crazy complicated process, but he couldn't do it by pen and paper. He had a computer do it. He had the computer start with the number 0. Then add some particular number z and square the result. Then he would add z and square the result. Add z, square the result, and so on and so on and so on. He would have the computer keep doing this until one of two things happened. Either the numbers kept getting bigger and bigger and bigger, or they didn't. If they got bigger and bigger and bigger, wherever z, see z is some number on this plane. Maybe it's 2 plus I, maybe it's 2, maybe it's whatever. If that number, when you square it and add, when you take 0, square it and add the number, then square that and add the number, and square that and add the number. If that gets bigger and bigger and bigger, you don't put a dot there. If it doesn't get bigger and bigger, if by some chance, probably because of this weird squaring to be a negative number, it kind of hovers within a particular range, not getting too big, then you do put a dot there. And when he first ran this computer program to see what the dots would look like, it was this smear on his computer, and he thought something had gone wrong. No, he had discovered something pretty freaking cool. For example, let's say we start with the number z equals 1/2. This is on the real axis. It's not 2, it's not 1. Right here. Do we put a dot right there? Well, you start by adding 1/2 to 0, and you get 1/2. Then you square that and add the 1/2 again. 1/2 squared is 1/4, and 1/4 plus 1/2 is 3/4. Then you square the 3/4 and add 1/2, and you get 17/6. And then you take the 17/6 and square it and add 1/2, and you get like 1.6. And you square 1.6 and add a half, and you get something. And you square that and you add something. Well, once you get 10, and then 10 squared is 100, and you add a little half. These numbers are going bigger and bigger and bigger, so you do not put a dot right there at 1/2. And it's hard enough to do that for one single point. To do all of the points in the entire plane takes a tremendous amount of computing power, but with a computer you can do that. With pencil and paper, there's no way you could do this. Anyway, in the future, after his initial project, he was originally using a black and white computer, they got to the point where for those weird points that don't go off, get bigger and bigger and bigger. Some of them stay quite small, some of them stay medium small, some of them stay big, but they don't go off to infinity. They would use different colors to graph these. And there is some computer programs to do this. I'm going to put a link to this website. There's plenty of them out there. A Java Mandlebrot applet. Pick the size, turn it off from autopilot onto manual because it's so much more fun. Choose your colors that you want to deal with. You probably don't want crazy, horrible things. Maybe you want sort of a purple or a blue. I'm going to start with a fire because it seems pretty awesome. You hit go. This is the smear that Mandlebrot saw, only he saw it in black and white. And it's just ridiculously complicated. Look at this shape. It's got sort of a bum. I don't know. It's got this point sticking out. If you zoom in on some part, you will see it has infinite detail. And this is what I was talking about, why trees aren't necessarily. And here it is, zooming way in on one little part of it, you see a copy of it itself all over again. Let's see, this little speck way over here, I bet, it's another one. This is a classic fractal. It has copies of itself inside of itself. Are there more? And there aren't only those, but there's crazy other stuff. Crazy, wild other stuff. This is the source of many a hallucinogenic dorm poster. Crazy, crazy, crazy things. I think we can zoom out. I don't know how to zoom out. Yes, I can zoom out. Zoom back, zoom back. So, pretty fun. And I would love to have you explore this. Look at some of the fringy stuff. Look at how many copies. It has infinitely many copies of itself, inside of itself. I'm done geeking out on this. That's enough for fractals for today.